if P divides A times B, then we want to show that P either divides A or B or both. So this is where P is a prime and A, B are both positive integers. It also works for negative integers, but it's of the same effect. And if A and B were 0, then of course it's obvious. So this result is a well-known result from elementary number theory. And so I'm gonna just look at a proof that I just found from a textbook, which is fabulous. So the proof goes like the proof by contradiction. So we assume that there is some prime number that even though divides A times B, but does not divide either of them. Right? So there must be a minimum P according to the well-ordered principle. There must be a minimum prime of course positive prime P naught, let's call it P naught fixed, so that even though P naught divides A times B, but P naught does not divide A, and P naught does not divide B. Right? And A and B could be many possibilities. Doesn't have to be fixed, right? Could be 5, 10, 11, 25. And out of the many possibilities, I say there also has to be a minimum product. Let's say minimum product A1 times A2, where P naught, even though divides A1 times A2, but P naught does not divide A1, and P naught does not divide A2, where A1 and A2 are fixed, and the product is the minimum, also according to the well-ordered principle. Right, so we're going to reach some contradiction from there. So if that's the case, I'm going to make the following claim that A1 has to be smaller than P naught. Of course, bigger than 0. And also at the same time, A2 bigger than 0, smaller than P naught. If otherwise, if let's say A1, for example, if it's bigger than P naught, it cannot equal to P naught, because if it's equal to P naught, then automatically P naught divides A1, right? So if that's the case, we can do some division. We can say, okay, A1 divided by P naught gives me some quotient, Q1 times P naught divisor, plus remainder R1, where, of course, remainder has to be bigger than 0, cannot equal to 0, otherwise that means P naught divides A1, right? Cannot be. And strictly smaller than the divisor, P naught, for the same reason. Now, since I assume P naught is smaller than A1, right? Smaller than A1. So R1 smaller than A1 in this case. So also I can tell that P naught cannot divide R1. Why? Because if P naught divides R1, also P naught divides this term, so which means P naught divides A1. Cannot happen. So this is automatic, of course, true. So in this case, I again have the ordered pair, have this pair where R1 times A2 gives me what? R1 times A2. R1 is equal to, first of all, A1 minus Q1 times P naught. times A2. That's A1 times A2. And minus Q1 A2 P naught. So that tells me, first of all, P naught divides A1 times A2, this term, right? Also, P naught divides this term, of course, divides the difference. So, which means P naught just divides R1 times A2. Now, in this case, also P naught does not divide R1. Also, P naught does not divide A2, right? So again, the R1, A2 satisfies this condition, right? And also, R1 times A2 smaller than, because R1 smaller than A1, therefore smaller than A1 times A2. So already contradiction, because I say A1, A2 is the minimum product. Somehow I found another smaller product, R1 times A2, also satisfies this condition. Right? Also satisfies this condition, so contradiction. So that's why this is true. And also, now what's going to happen? And of course, for the same reason, right? This is true. For the same reason, this is also true, right? If we just do the same thing to A2, right? For the same reason. So then I can say A1, A2 can be written into, because P naught divides A1 times A2, therefore can be written into some constant time, some positive integer times P naught. C is some positive integer. That's what it means by divides, right? So in this case, I say C must be strictly greater than 1. Because if C was equal to 1, what's going to happen? A1 times A2 equals P naught. Right? But P naught is a prime. P naught is a prime. So meaning A1, A2 cannot be both primes, right? At least one of them has to be exactly equal to P naught in this case, which is a contradiction. So C has to be strictly bigger than 1. And strictly because A1, A2, like I said, both smaller than P naught. Therefore, multiply together strictly less than P naught square. So in this case, C has to be strictly less than P naught. Also, in this case, that tells me C must contain some prime factor. P1 divides C. C itself could be a prime, or if C was a composite number, then it has to contain some prime factor. First of all, C does not equal to 1, so that we're already safe. C could be 2, could be 3, whatever. There at least one prime, right? That's in C. Of course, where P1 is smaller than P naught, obviously. So in this case, P1 already smaller than P naught. And also, P naught is like I said, it's a minimum prime that satisfies this condition. All right, so, which means any prime that's smaller than P naught does not satisfy this condition, meaning even though P1 divides, first of all, divides C, of course, divides this thing, divides A1 times A2, which means P1 divides at least one of them, right? Because, like I said, P naught is the minimum prime that satisfies this condition. So any prime that's smaller than this one will will divide AB, but divide at least one of them. So in this case, I say P1 divide at least one of them. Maybe, for example, divides A1. Right? I say A1 divided by P1, that's an integer, times A2 equals, divide by the same thing on the right-hand side. C divided P1, also an integer, right? Times P0. So in this case, actually P0 divides integer times P0, which means P0 divides this thing, right? Divides A1 over P1 times A2, right? So in this case, I found another pair, right? P0 divides their product, except in this case, P0 again does not divide A2. Does not divide A2. Also does not divide A1 over P1. Because if it does, then that means P0 divides A1 also, right? Which is impossible, right? So that means I found another two positive integer where they satisfy the same condition. Satisfy the same condition. They divide their product does not divide either of them. Right? In this case, this positive integer, that positive integer, but this positive integer already smaller than A1. Right? Which means their product has to be smaller than A1 times A2, which is a contradiction. Like I said, A1, A2 already the smallest, and that's a contradiction. Contradiction. So which means really, assumption is false, right? Meaning if P divides AB, means P divides at least one